Okay, well, thank you for coming, and thank you for the opportunity to talk. So, I'm speaking to actually some people who are definitely experts on these sorts of things, but I want to start at the beginning. So, some background. Poincaré series. On GL3. Okay, so my G here is always going to be PSL3R. Gamma is SL3Z, and even though this is not strictly a subgroup of that, this is made of cosets mod R, but anything that injects in there, I'm just going to call it by its own name. So I'm going to think of this thing as a subset and move on. Okay, so I have individual pieces. I had a couple of decompositions, the Iwasawa decomposition and the Bruhat decomposition, and those things are formed of pieces. So first of all, the most important thing here is going to be this SO3R. Yeah, the maximal compact subgroup. We have U of R, the upper unipotent matrices. So this is 1, 1, 1, X2, X3, X1, where these things are in R. Okay, and then the diagonal matrices, but diagonal matrices in here, I want to write them sort of with a 1 in the lower right-hand corner. So Y plus the space of matrices of the form Y1, Y2, Y1, 1, where these guys are positive, Y2 and R plus. Okay, and I need a couple more groups. So the diagonal matrices in here, these are V is the set of matrices V epsilon 1, epsilon 2, where epsilon 1 and epsilon 2 are plus or minus 1. And this is epsilon 1, epsilon 1, epsilon 2, epsilon 1. Okay, the group. And lastly, the Weil group. There are 6 things in here. They're the permutation matrices. And the only one that I actually care about right at the moment is the long element. So this is 1, 1, 1, 0, 0. Sort of the anti-diagonal thing. Okay. So characters of this space, and then the representation theory of that space. Okay, so first of all, characters of things in here, which I usually call X, okay, look like psi, let's call this T of X is E of T1 X1 plus T2 X2, where T is in R squared, and E of, well, T, call it something else, E of X is e to the 2 pi I x. Okay, characters of this space are given by the power function. So P mu A1, A2, A3 is abs A1 to the mu 1, abs A2 to the mu 2, abs A3 to the mu 3. And if I want this function to be defined on diagonal matrices in G up there, I need for these things to sum to 0. Okay. Lastly, characters of that, of V, that is the Klein 4 group, and its character table is also the Klein 4 group. But these are things like this. This is, let's see here, what I want to call this. I want to call this minus plus of V epsilon 1, epsilon 2 is epsilon 1, and chi plus minus V epsilon 1, epsilon 2, epsilon 2, and then products of those characters. Okay. Lastly, the representation theory of K, there are no characters beyond the trivial character, but it's completely parameterized up to isomorphism by the Wigner D matrices. So this is my attempt at a script D. And there is one of these for every odd dimension D. So D is some integer greater than or equal to 0. Okay, and I'm not going to care too much about the contents of those matrices, but yeah, this is well known. So SO3R is the space of rotations in 3 dimensions, so physicists have studied these things in great detail, and I don't need to repeat those. Okay, so with these things, I can define a Poincaré series. Okay, so if you give me a function, see for a moment, let's say it's scalar valued, but eventually I'm going to talk about vector valued for functions here. And I would like this function to satisfy that on the left-hand side, if I put one of these elements of u of r in there, it should transform by, let's call it psi m of x f of g. Okay, Goldfeld calls these an E psi m functions. Okay, and from this, I can define a Poincaré series Pf of g is just the sum over gamma in gamma mod u of z of f of gamma g. And so that is the Poincaré series associated to f. Okay, so far I'm only assuming that on the left-hand side it transforms by a character. I said nothing about what happens on the right-hand side. But if it on the right-hand side is not a function of k, I call this thing spherical. Okay, where g is an element of g and k is an element of k and so on. Okay, so far so good. All notation. Hopefully my notations may be a little strange, but this shouldn't be that weird. So. Yes, yeah. So most of this talk, actually pretty much all of this talk, I really only care about I really only care about this right at the moment. So you can do all of the things that I'm about to do with degenerate characters, and you get sort of interesting things, but I don't want to deal with that right now. And in fact, I'm going to fudge a number of details here and there, I'm sorry. But so just let me say, I don't usually use this in this form. I would like to translate this. So this is 1, 0, minus 1. Then the power function at rho plus mu of a matrix in here. This is y1 to the 1 minus mu 3, y2, 1 plus mu 1. And that's normalized so that the line of symmetry, whatever you want to call it, is at the 0 line. So real of mu equals 0. This is tempered forms and all of those fun things. Okay, so what do we know about these Poincaré series so far? Okay. My interest in these Poincaré series is that you have both a geometric interpretation of their Fourier coefficients and a spectral interpretation of the function itself. And so if you connect those two things, you get something called a Kuznetsov trace formula. So the Bruhat decomposition, how am I doing? Good. Okay, the Bruhat decomposition sort of non-uniquely looks like this, that G is U of R Y plus V W U of R. So everything in here can be written as a product of matrices in this form, but not necessarily uniquely. Okay, and you can enforce uniqueness actually in the following manner. So if you split U up into two pieces, the piece that when you conjugate across a particular Weyl element lands inside U again, or the piece that lands outside of U. Okay, so those two pieces look like this. So for each W and W, you can define UW. Okay, I always get these things backwards. So this is U intersect W inverse UW. Okay, that's a subscript and that's a times a W. Okay, and then UW bar is U intersect W inverse U transpose W. Okay, and for each W, this gives you a factorization of the full group. Okay, so every coordinate in W in U lands in either UW or UW bar, and this gives you a unique Bruhat decomposition, which is the union over W and W of U R Y plus the little w U W R bar. Okay, so if you take this decomposition and you apply it to this gamma, you have, a very non-explicit version of this theorem of Bump, Friedberg, and Goldfeld. So this is theorem okay, so that Poincaré series over there, PF of G, is the sum over, well, here it's the sum over V and V, the sum over W and W, the sum over, so my diagonal matrices are given by two integers, and I can make them non-negative of what? Okay, so that's, oh, oops, sorry. I was supposed to take the Fourier coefficient here. So let me take the Fourier coefficient. So the Fourier coefficient of this thing with a character in here is psi n of x bar dx, and then put an x here. Okay, so these are the Fourier coefficients of these things. That is equal to, and that's where the n comes from, CV times an integral, and let me write the integral, UW bar of R f of C V W x G psi n of x bar dx. Okay, so these are the finite places, and here is the Archimedean place. And these sums here, they're generalizations of Kloosterman sums. So Sorry, I'm not Dutch or which? CV. So I'm writing this thing a little bit oddly, but that is the sum over matrices in gamma who have Bruhat decomposition involving CV and W. Okay, so this is BCVWB prime in gamma mod U of Z mod UW of Z bar of, so that was the summation condition, psi m of B, psi n of B prime. Okay. And you can, in fact, show that this mess is actually an exponential sum, okay? And you can work out what that is. The most important one from the theory of using these things is actually when WL is a long element. And when WL is a long element, this UW bar is actually just U. Okay, and the same. Okay, and I guess I never said C was particularly this matrix. 1 over C2, C1 over C2, C1. Sorry, C2 over C1, C1. That diagonal matrix in particular. Okay, and so that is the Bruhat decomposition side. Okay, so this is the geometric side of what's going to be a sort of trace formula of Kuznetsov type. All right, so far so good. All right. Okay, so well, one last point. There's a sneaky technical detail that you should define this thing to be 0 if this product depends on Bruhat decomposition. Okay, so if you use the non-unique Bruhat decomposition here, then this product should be independent of the choice of Bruhat decomposition, and if it's not, just define the sum to be 0. Okay. Okay. So the other side. Okay, so we have a geometric interpretation of the Fourier coefficients.
I mean, those are, depending on what W is, are products of ordinary closed. You have 2 closed-amount sums and a you have 3 closed-amount sums for some other elements, right?
Yeah, so for the long element, they're a sum of products of 2 classical Kloosterman sums. And for the other non-long element cases that aren't degenerate, they're basically the hyper-Kloosterman sums. Okay. Okay, so how do you get, oh, there it is. Mumfriedberg and Goldfeld didn't actually literally prove this. They proved this in the case where F is spherical. Okay, and the whole point of the talk here is where F is not spherical. So with a spectral decomposition, you sort of need to understand what the spectral side of L2 of G mod gamma with no right quotient by K. So the spectral decomposition in G mod gamma, L2 of G mod gamma, okay, so the spectral decomposition. Okay, so this is in there. Okay, so there's 2 pieces that we like to have. We want Maass forms to be eigenfunctions of the Casimir operators. So these are the 2 differential operators. They generate the center of the universal enveloping algebra. And the other thing that we would like is we would like them to be sort of uniform in respect to the representation theory of K on the right-hand side. So, okay. Okay, so this thing, so these are scalar valued functions, and I would like to switch to vector valued functions, then I'll talk about those, and then I will come back to scalar valued functions again. So first of all, you have two differential operators. I said delta 1 and delta 2. Okay, so these are the Casimir operators. Okay, and I would like to talk about vector-valued Maass forms. So A, it's my attempt at a script A, D, and I should really put a 0 down here. Okay, and I want to define what I mean by this space. It's the space of automorphic forms that transform on the right-hand side according to the Wigner D matrix, and or cuspidal, and so on. So, okay, means. Okay, one. Okay, so this is a function. A 2D plus 1 dimensional row vector valued function. Okay, its K type should be one of these Wigner D matrices, in fact, that Wigner D matrix. So we have f of gk should be f of g d of k. I'm transforming on the right-hand side, okay, because I'm taking the quotient of gamma on the left-hand side. Okay, so 3, it should be square integrable. So the integral over g mod gamma of f of g bar transpose dg should be less than infinity. Okay. 4, so it should be cuspidal. Okay, and so I sort of belatedly defined what I meant by a Fourier coefficient. So I mean by cuspidal that all of the degenerate Fourier coefficients of f are 0. So all Fourier coefficients with n1 times n2 equal to 0 are 0. Okay. And there's also a boundedness condition, but it's sort of technical and I kind of want to ignore it. But this space here, it has a basis of Maass forms, and Maass forms are eigenfunctions of these two things. So 5. So Maass forms. Okay, so Maass forms are elements of this space that satisfy a fifth condition, and that condition is that delta I f equals lambda I of mu f. Okay, where these eigenvalues are specifically the eigenvalues of the power function at mu. Okay, so lambda 1 of mu is, so this is 1 minus mu 1 squared plus mu 2 squared. It's mu 3 squared over 2, and lambda 2 of mu is mu 1, mu 2, mu 3. Okay, so those are the eigenvalues of the power function under the Casimir operators. Okay, so we have automorphic forms of weight k and Maass forms of weight k. And from this I can build a basis of actually the L2 space of G mod gamma, but I need to say a little bit. So using sort of fundamentally this Shalika's multiplicity 1 theorem, I want to talk about these functions as in terms of their Whittaker functions. And I also want to describe what the Lie algebra looks like on these things. So I don't want to go too in depth on the Lie algebra, but the Lie algebra.
Basic question. These linear D matrices, I'm not really familiar with them. It's just a representation of.
Yeah. So they exhaust the isomorphism class of irreducible unitary representations of K, SO3. Okay.
Just writing down the K type and running the functions in a K type basis.
Yes.
You don't want to use Langlands parameters because then we'll recognize where everything's unitary.
Okay.
It's not important, but if you ever generalize to another group, it might be useful.
Okay. But the Lie algebra of G, so I
Did Wallach define Poincaré series for a general G?
Didn't Wallach define Poincaré series for general G?
But probably he put in for the function of y, which you put in arbitrary function, I think he put an eigenfunction. He got into some very interesting and difficult problems about exponentially growing Whittaker functions. Did you study that? But he never wrote down a Kuznetsov for me. He just expanded P.
Yeah. So I don't know about the exponentially growing Whittaker functions, but yeah, I've seen Wallach's. Yeah. Okay. So the Lie.
He did define Poincaré series in general. That's
Yeah.
ordinary notation.
So the Lie algebra. So the reason why is sort of vaguely because the dimension of the Lie algebra of G modulo the Lie algebra of K is 5. So you end up with 5 operators going between these spaces, and so you have to. It's easiest to use some sort of projection operators because the Lie algebra wants to sort of mix things, which is really annoying. But for each D, you can construct from the Lie algebra and maybe some projection operators on K, 5 operators that are raising and lowering operators. So A goes from -2, -1, 0, 1, and 2. Okay. So I'm not going to construct them. It's a little messy, but you can do this. And then we're going to say M form is minimal weight. Say F in A D0 is minimal weight. If one of the 3 following things, 3 equivalent things, happens. If any of.
So these operators, you apply something to the algebra and then you project to a K type.
Yes. Yeah. So at each D, it's possible to take a linear combination that does the projection for you, but the construction of that linear combination is a little bit annoying with Clebsch-Gordon coefficients, and it depends on D. Yes. But it's a little easier if you just project. But so I'm, yeah, so, yeah, okay. That's enough about that. So the following 3 things are equivalent, okay? So first of all, if F is orthogonal under that inner product to all of the lifts, okay, so this is Y1 A D minus 1 0 and Y2 A D minus 2 0. Okay, or equivalently, F is killed by Y minus 2 and y minus 1, and it's an eigenfunction of y0. So y0 doesn't change the k-type. It just sort of stirs things around. And third, so this is strangely handy, okay, good. Strangely handy criteria. So either d equals 0, d equals 1, or so lambda d minus 1 over 2f is 0, where this lambda differential operator, so it's specifically constructed to kill forms with Langland spectral parameters in a particular form. But here is that operator. It is this. So lambda x is 27 delta 2 squared plus 4 delta 1, that's a 1, plus x squared minus 1, delta 1 plus 4x minus 1 squared. Okay. Okay, and that may seem strange, but these other types are talking about what goes on when you change the k-type of something. So to identify a minimal weight form, the top thing is definitely the hardest because you have to sort of lift everything and see what's orthogonal to it. The second one is a little bit easier. You have to say, okay, what's killed by all of these things? And this one is the easiest. It only depends on the eigenvalues of f. Okay, so if f is minimal weight, I'm going to put a little star to the left, right of d. Say a d star equals minimal weight forms. Okay, space of minimal weight forms. Okay. Okay. So, Shalika's multiplicity. How do you say that? Is it Shalika or Shalika? Shalika. Okay. Thank you. Shalika's multiplicity 1 theorem basically says that for forms that of the form that I'm talking about, their Fourier coefficients, they lie in the span of the Jacquet integral. They're given by Jacquet integrals of functions in K and the power function. So for each D, I can construct a sort of matrix-valued Whittaker function that looks something like this. So you say I d of x, y, k is, and maybe I should say mu here, p rho plus mu of y times the Wigner D matrix. Okay, and I stuff this into this integral that Jacquet considered. So I'm going to call this WD, WD of G mu, and some character of the x component is the integral over u r of I d mu of WL x G psi of x bar dx. Okay, and this gives me a matrix-valued Whittaker function. It's kind of handy to consider these things in matrices because the functional equations then are just matrix multiplication. And specifically, the Fourier coefficients of these things if F is a vector-valued Maass form of minimal weight, say F a Maass form, okay, this implies that either, okay, so its Fourier coefficients are, let's see here, so what is this? This is some vector, let me call it UD of WD dot mu psi n. So its nth Fourier coefficient is a multiple of this, where this mu is the mu that came up in the definition of the Maass form, and this UD, okay, so if d equals 0, then it doesn't matter, UD is just 1. You take UD equal to 1. And I can say something about the spectral parameters mu. And so either mu is of the form x plus it minus x plus it minus 2it, or it has real part equal to 0. And the Ramanujan-Selberg conjecture is that that happens and that does not. I can say also here, as x is less than 5/14, and that is by Kim Sarnak. So this is the spherical forms. Okay. Okay. If d equals 1, then mu is of the same form. It's either x plus it minus x plus it and minus 2it, or equal to 0. And ud, I can choose 0, 1, 0. I can choose that up to permutations, functional equations of the Whittaker function. And lastly, if d is greater than or equal to 2, then, well, I'm going to take, I can choose again that this is minus 1 to the d, 0, 0, 1. And I know that mu, for this permutation for this functional equation of the Whittaker function, this is of the form d minus 1 over 2 plus it minus d minus 1 over 2 plus it and minus 2it. And t is real. Okay, so in terms of the representation theory for automorphic forms, okay, these things are spherical representations. These things are non-spherical principal series representations, and these things are generalized principal series representations induced from the levy, the 2-1 levy. Okay? Yes. Yeah. Yeah. So they are non-principal generalized principal series representations. Okay. Okay. So that tells me what their Whittaker functions are at each minimal k-type. And then what I want to do is I want to take this and build a basis for L2 of G mod gamma by arranging the vector-valued forms into matrix-valued forms. Okay. So
Are we doing all this because you're going to give some inversion in the letter form?
yes. Yep. Okay. So how am I doing? Okay.
Look at the relative trace multiplication in here. The inversion, even in the ordinary case, was all that Kuznetsov actually did. That was his contribution to get that right. You know that Titchmarsh got it wrong.
Yeah. Yeah.
You know it, I was mistake.
Sears is a.
Sears.
Yeah. Okay, so let me just say that each of these vectors, UD, they're a row of this matrix.
He taught me. He spent time in Australia, I think, so that's where you came with. Flounders with it. Flinders.
Okay, so the Whittaker function, the matrix-valued Whittaker function that I constructed is sort of the continuous part of the character of the diagonal, the signed diagonal matrices. This character, the character of the V group, is the discrete part of the character. Okay, and so if I take the Fourier coefficients of one of these vector-valued forms and I slap it on this a Whittaker function with this thing on the left-hand side. So let's say if I have, so if f is one of these minimal weight vector-valued forms, I'm going to associate to f a new fd of g, which is the sum over gamma in the c of z slash sl2 z v of, okay, so rho f of n sigma d chi w d of g mu psi n. There. So if I take the Fourier coefficients, I mean this, the Fourier Whittaker coefficients, this, and I put them in this Fourier expansion. Okay, so I can do this for every d. It just doesn't necessarily make sense. Okay, it doesn't necessarily give me that the rows of this thing are going to be cusp forms. On the other hand, if I consider this one, and I consider also, so this is not the dual form, but if I replace mu here with minus mu bar. Okay, and so our matrix-valued Whittaker function is not symmetric in mu. It's not possible to complete this thing so that it becomes symmetric in mu. So this is a permutation of that, but it's not necessarily a trivial permutation. Okay, so I define this function the same way as that. I just replaced that with that. Okay, and it turns out if I have one of these generalized principal series representations, it's supposed to be missing stuff. Okay, it's not supposed to hit everything in the principal series representation that it's a sub-representation of. And in this function, everything that's not supposed to be there is killed by that. Okay, so the incomplete Whittaker function is actually 0 at all of the pieces that are supposed to be missing. Okay, so from this, I can now write down a slightly strange but very complete spectral expansion. So I can say if f is well, let's just say sufficiently nice. So I mean like Schwartz class g mod gamma to c, so back to scalar valued forms. So say it's nice like Schwartz class, and also that it's cuspidal. So I don't want to get into the Eisenstein series at all, but the Eisenstein series are definitely more explicit, so you can actually construct the Eisenstein series explicitly from GL2 forms. But if this is true, then f of g is the sum. So the sum over all minimal weight vector valued forms of all dimensions. Okay, phi min weight of any weight. Okay. okay, a basis of things. Okay, and the sum over d greater than or equal to 0, greater than or equal to 0, of the trace of, so this is, what do I want to say? Pick your favorite one. This is phi d of g, the integral over g mod gamma of f of g prime phi d tilde of g prime dg prime, like so. Okay, and what's slightly strange about this is that for each minimal weight form, I'm going to sum these functions for all d. Okay, so it's very uniform. Okay, so what?
I'm trying to digest sigma sub gamma d. This sum is, it's 1/4 sum of v and d. Just explain that.
Okay, so it's 1/4 the sum of the diagonal orthogonal matrices. So there are 4 things in here, and I'm projecting onto the space of things that. Okay, this is a projection operator as a matrix, but I'm multiplying this as some character of this space. Okay, so this is plus or minus 1 for each v in here, and I'm summing actually the matrix, the Wigner D matrix. Okay.
What are you going to run out of time before?
Yeah. So, yeah, do I want to actually state that? Okay. So, yeah, I said it was ambitious. Okay, so.
I just think most people here may not know why this is even useful.
Yeah. Okay, so if you take a function that has, so some f, you have this Bruhat decomposition, and you have a spectral expansion for the Poincaré series, like that. And if I choose my f, actually what I would take my f to be a inverse Whittaker transform. I take my f to be an inverse Whittaker transform, and I take the spectral expansion of that. You can show that it's going to collapse to something of the form. So this same Fourier coefficient of the Poincaré series is going to be something, so it's a sum over minimal weight forms, phi minimal weight. And if I take these, to be vector-valued things, I'm going to get basically the Fourier coefficient of rho at n bar and the Fourier coefficient of rho at n. And if I choose my f wisely enough, I can force this to be some function of the Langlands parameters alone, and I can localize this so that phi has minimal weight, specifically whatever d I choose there. Okay, and so on this side, okay, and then there's plus continuous.
We're choosing 2 coefficients m and n.
Yeah.
Summing over the spectrum of d-type, minimal weight d.
Yes.
Weighted by some weird transform.
Yeah. So I can invert that transform so that this is my chosen test function.
That's an arbitrary function.
That's an arbitrary function.
Is there not an issue of where it lies? Is that maybe kind of?
Yeah. So you need for that side to converge.
Your mother function is little f.
Yeah. Yeah.
And that is used to generate, like in the trace formula, an identity.
Yeah.
That's one side of the identity.
Yeah.
Okay. What's the other side?
So this thing, but this integral. So what I'm literally going to do is I'm going to choose my f to be an integral over some family of mu of capital F of mu times the minimal weight Whittaker function. So G mu times some stuff d mu. And with this choice, it turns out that on this side I'm going to have the Whittaker transform of this inverse Whittaker transform, and you can show that that gives you your original function back. You do need holomorphy out to plus or minus a half for the weight 0 and 1, but for weight d greater than or equal to 2, you need holomorphy out to 1/4. Okay? And then on this side, what happens is that this integral over uw bar, with some severe effort, you can exchange this thing.
So that sum equals the sum of the C1, C2 problem, right?
Yeah, so this side. Exactly that for that.
The left-hand side of your formula is the sum of these phis,
Yes.
immanent coefficient. The right-hand side is the sum over all C1, C2.
Yeah, so the sum over all V, the sum over all W, and the sum over C1, C2 of those sums with this integral, but I claim that you can write that this integral is this integral over mu, f of mu, times some kernel functions of C, CV, and mu, times some gamma functions and d mu.
It's going to be sums of Postman sums weighted by some complicated transform of capital F that's
Yes.
entirely explicit.
Yes, entirely explicit. All right, we're doing, well, okay.
And can you invert the other way around?
So you
Put a function on the Postman sum?
yeah, so you can put an arbitrary function on the long element Kloosterman sum. Okay, if you try and put it on one of the other Kloosterman sums, you get something that's almost everywhere 0. So it's not an L2 thing. But you can put an arbitrary function on the long element Kloosterman sums. And, well, in one case of the signs, I have explicit the transform. In the other case, I can say it's an integral of your test function against some function, and then my expression for that function is just too horrible to mention. But I'm working on that. Okay.
So at this point, you're inverting it from the side of the sum over the spectrum
Yes.
in terms of Postman sums.
Yes.
Explicit.
Okay. And so, my talk was perhaps a bit too ambitious because what I was actually invited to speak about was sub-convexity for GL3L functions. But yeah, but you can use this to show sub-convexity for pure GL3L functions with no twists.
Show that state theorem.
State the theorem. Okay, so theorem. Okay, so if phi is one of these functions, so a d star 0 Maass cusp form. Okay, and then to such a thing, there is an L function constructed as Dirichlet series constructed from these things, or its Hecke eigenvalues better. Okay, then its L function. So L, do you go S phi or phi S? L S 1/2 at the central point, the critical point, is bounded by, okay, I'm going to write t here, I'll explain t here in a second, 3/4 minus 120,000th for d equal to 0, and for d greater than or equal to 2, the same thing is bounded by t to the 3/4 minus 140,000th, where t is basically the norm of mu, but subject to the restrictions that phi's mu is away from the Weyl chamber walls and away from the self-dual forms. So mu I squeeze t and squeeze mu I minus mu j. Okay, so specifically away from, well, probably the thing everybody wants to make this work for. But yeah, so the 3/4 is the convexity bound for this thing. And we have indeed saved, well, you can put a plus epsilon there, but you know, whatever.
You work a little harder, and that number's so small.
Yes. So yeah. Yeah, that's probably
so your method is to average.
Yeah, so it's a local average of the 4th moment of these things. So it's an average. I erased the. So here, there we go. If you take f to be supported in a ball of radius 1 around your favorite form, and then you average the 4th moment of these things. So it's a local 4th moment. And, well, I mean, the 2 chunks that go into it are some sort of Archimedean analysis. You need a sharp cutoff for the sum of Kloosterman sums.
Averaging the spectral parameter in a neighborhood in this interior of the Weyl chamber. So that's like a barbell.
Yeah.
If the coefficients n and m were both 1, you would just be counting the number.
Yes. Yeah.
The mileage, you take the 4th power.
Yes.
So when you take the 4th power, you take an approximate function equation, 4th power.
Mm-hmm.
You get products of, you get a lot of.
Yeah. So you use the Hecker relations to get something that looks like this, where M1, M2, N1, N2 are all about size t to the 3/2, and then
you plug in this formula.
Yeah, you plug in the Kuznetsov
On the other
formula.
side, you just use base bound for Kloosterman sums.
No. So you do a 4-fold Poisson summation. M1, M2, N1, N2. Yeah. And there's some sort of an amplifier going on. But I just wanted to say one thing. So
The amplifier is not really needed. You shorten the range. You just shorten.
No. So the number of things in that ball are t cubed. And we're taking the 4th moment. So we need to be 3/4.
Okay.
Yeah, that is.
Short polynomial with that on top of it.
Yeah. So an amplified local 4th moment. But so the Archimedean analysis part of this thing is to show that these transforms have a sharp cutoff in C. So they decay very rapidly past the point, well, in this case, I think it's like C1, C2 of size t, I think. And then after you do the Poisson summation, you have this horrendous integral that you want to try and bound. It's the 4-fold Fourier transform of that, okay? And what we did was we just used the Malin expansion for these things. So I gave Malin-Barnes integrals for these things. And the nice thing about using the Malin transform like that is that the number of Poisson summations doesn't matter. So if you have 2 or you have 200, it works the same because yeah, you're taking products of these things inside the Malin transform. It works very nicely. But that last thing is getting an upper bound for basically a 2-dimensional Malin-Barnes integral, sort of from Stirling's formula, and it's super technical, but yeah, it works.
But the only way in this application is just to put f, a local bump function, to localize this spectrum.
Yep. And so I said radius 1, but I really mean like radius t to the epsilon. So you just get a little bit of help in the Archimedean place. Yep. So that's good. Thanks.
Since you have an opportunity here to advertise it's mentioning other applications.
Oh, yeah, so,
What I'm interested for those people here working in trace the tension between disconnect that.
yeah, so, okay, so you have,
Stress to Lapid who just left.
okay, so you have, the simplest application of these things are Weyl laws, okay? And for the Kuznetsov type formula, you can get a very strong Weyl law, but with arithmetic weights, okay? So you have a very strong error term, usually stronger than what comes up in the Weyl law without the weights that comes from Selberg trace formula. So you get a very strong Weyl law. Other things that you can do with this, you can show that the number of exceptional eigenvalues in either the place at infinity, so in mu, or in the finite places, you can give a density estimate on the number of exceptional eigenvalues, the number of exceptional Langlands parameters, the number of exceptional Satake parameters. What else can you do? Well, we have large sieve estimates. Those were fun. But what else should I be saying?
So they all involve this putting, they always, in all those questions about rho phi and rho phi n, you put m equal n there, and you analyze the right-hand side using, in that kind of problem, you're probably just using
The Weil bound, yeah.
You don't need the Wien's bounds, probably, because there's so few terms in that. Is that correct? In other words, the bound elements which involve the hyperclose.
It definitely involves less work, but I think you do still need a little bit of effort on those terms. So certainly in these problems, you're just using a bound, and well, I think we had Larson's bound, so we used Larson's bound. But do you strictly need it? I don't know off the top of my head.
In your theorem, can you fix the range of the spectral parameters in that D there?
Yeah, so no. These mu's, so this statement needs to apply in both cases. Okay, and these mu's involve D. Okay, and in fact, this one is saying that actually D is of size T as well. So you have to vary both D and this imaginary IT in the mu. They have to both be big. And if you get too far away from where they're the same size, then things start to...
In your language, when the way where people vary the vector in the representation is actually varying it non-trivially, it's kind of shearing it.
Yeah. Well, I'm varying what the minimal weight is. Yeah. Yeah. Okay. Thanks for coming.
More questions? If not, then let's thank speaker here.